Hi everybody, welcome back to my channel on Feynman integration. Happy New Year, and we're going to start the new year off with quite a difficult integral. Give me 1 second. A little bit more light in here, there we go. Okay, so the integral we're going to be doing is one that I got off of the channel, let's see, QNCUBED3. I'm not sure what that stands for, but it's run by a young fellow that likes to focus on contour integration. That's not my favorite method of integration. I'm barely competent at it, but today we'll be solving it with Feynman's technique, using the Leibniz rule for differentiation under the integral sign, as always. So the integral we're talking about is this one. It's the integral from 0 to infinity of the natural log of x to the 4th plus 1 over x squared plus 1 dx. And in this video, and I think also in future videos, what I'll be doing is I'll be writing out the main steps on this side, and this side will kind of be used as a scratch pad. I'm going to be solving this from start to finish, doing every step along the way on the board for you. Okay, so what's generally the first thing we do using Feynman integration? We would reparameterize that. What would jump out at you right away is maybe to insert a t there or replace that 1 with a t. Maybe some of you can try it. I've tried it. I didn't have much luck doing it that way. This is what I came up with. Since we know by the properties of logarithms that the natural log of a plus the natural log of b is equal to the natural log of a times b, we can rewrite that natural log of x to the 4th plus 1 like this. We could call it the natural log of x squared plus I plus the natural log of x squared minus I. So that's what we're going to do. We're just going to put this over there and call it 2 separate integrals, and the integral will be equivalent. So now we have a new definition of I, which is equal to the integral from 0 to infinity of the natural log of x squared plus I over x squared plus 1 dx plus the integral from 0 to infinity of the natural log of x squared minus I over x squared plus 1 dx. All right, so that's totally valid. So what next? Now we can make a reparameterization, and we'll just use one of them to reparameterize, and we'll replace that I there with a t. So our f of t becomes the integral from 0 to infinity of the natural log of x squared plus t over x squared plus 1 dx. All right, how are we going to get back our original integral? It should be fairly obvious. Our I will be equal to our function f evaluated at the imaginary unit plus our function f evaluated at the negative imaginary unit. So usually as part of this step, when we first create our new function in terms of t, we like to find a value for t that will make the integral very easy to solve. Therefore, we can have like an f of 0 is equal to something. In this case, it will be f of 0. That's about the only thing I could come up with that would make that integral doable fairly easily. And what you get if you do that is 0. And that might not be obvious right off the bat that that integral would be equal to 0, so I'll show it to you right now. Let's call a new integral j. It's equal to the integral from 0 to infinity of this thing evaluated at 0. So right away, I'll use the properties of logs to bring out that squared on the x, and we'll just call this natural log x over x squared plus 1 dx. Then by making the substitution x is equal to 1 over u, we get that j is also equal to 2 times the integral from, well, let's see, that would be infinity to 0 of the natural log of 1 over u over 1 over u squared plus 1 times negative 1 over u squared du. And you see, if you simplify that out, you distribute this u squared to there, you'll end up with a u squared plus 1 on the bottom, just like here. We can use properties of logarithms to just make this a natural log negative, or a negative natural log u, which will cancel that negative sign right there. Then we can switch the bounds to introduce a negative sign, making j equal to negative j, therefore j is equal to 0. So that's the explanation of why that thing is equal to 0 at 0. All right, next step. Take a derivative with respect to t of our new function of t. So f prime of t would be equal to the integral from 0 to infinity of, let's see, that's going to be 1 over, the derivative of this with respect to t is 1 over x squared plus t. And that's it, that's all it is. So we have 1 over x squared plus 1, x squared plus t dx. All right. Now, maybe you can solve that directly with a trig substitution. It'd probably be pretty difficult. I think the most straightforward way to do that is to use partial fractions. So we know that this integrand right here can be written in the following way. Some constant ax plus b over x squared plus 1 plus some constant cx plus some constant d over x squared plus t must be equal to 1 over x squared plus 1 times x squared plus t. So now we just have to cross multiply and match up terms. So what's our x cubed terms? We'll have a and c for our x cubed terms on the left hand side, and 0 for our x cubed terms on the right. Likewise, with our x squared terms, we would have b plus d being equal to 0. Also, we would have a t plus c being equal to 0. And finally, we would have bt plus d being equal to 1, because those are our constant terms, and we do have constant terms. All right, well, from this we can see that c is equal to negative a. Let's go ahead and plug that in right here. And then on this one, you can see that by factoring out an a and then dividing both sides by t minus 1, you'll have that a is equal to 0. Therefore, c is also equal to 0. Therefore, we can just get rid of these terms right here, because they will not be included. All right. From this, we see that d is equal to negative b. We'll plug that in right here. Factoring out the b and dividing by t minus 1 on both sides gives us that b is going to be equal to 1 over t minus 1. I'll just put that in there right now. And that d will be equal to negative 1 over t minus 1. 1 over t minus 1. There we go. All right, so that's a true statement right there. We know that this is equivalent to this. So we can rewrite our f prime of t using these two things instead of that one thing. So let's just go ahead and do it. right, so what's that going to be? That's going to be the integral. Well, no, first I'll just bring that 1 over t minus 1 right out, times the integral from 0 to infinity of 1 over x squared plus 1. That's going to be an easy one. Minus 1 over t minus 1 times the integral from 0 to infinity of 1 over x squared plus t dx. All right, we're going to focus on this part of the problem right now, because this part's easy. This part, pretty easy too. In fact, probably some of you could just tell me in your head what that is, but I'm not good at memorization, so I'm actually going to have to do a trig sub for that. And I'll do that on the board for you right now. I really should get those memorized, but I haven't. All right, so since we're doing a trig sub, we will create a triangle. The most obvious thing to do is to have the hypotenuse. Since we have something plus something else, we'll have the hypotenuse equal to the square root of that thing. Since the hypotenuse is always going to be the longest side. And then we'll put an x here and the square root of t there. And we'll call this angle theta. All right, so from that, we see that tangent theta is x over the square root of t. That means square root of t, tangent theta, is equal to x. Therefore, square root of t, secant squared theta, d theta is equal to dx. And for now, that'll be good enough for us to plug in some values. So we're just working on this part right now, don't forget. So we'll have the integral from, let's see, 0 would make theta equal to 0, and infinity would make theta equal pi over 2. All right, so we have the integral from 0 to pi over 2 of, let's see, we'll put in our dx. That's going to be square root of t times secant squared theta d theta, and then it's going to be over something. What is x squared plus t in this triangle? Well, let's see. We know that x squared plus t over t is equal to this over this squared, and that over that is secant, so that's equal to secant squared theta. So that's secant squared theta. And then we'll just bring this t over here. And now we have what x squared plus t is. There we go. So that's just going to be t, which I will put right here. Secant squared theta will cancel this. So we're just left with a d theta, giving us 1 over the square root of t times pi over 2. Yeah, that's it. All right. So now let's just go ahead and rewrite our f prime of t below here. So now we have f prime of t is equal to, all right, so this is going to be pi over 2 times 1 over t minus 1. This is going to be negative, let's see, it's going to be the exact same thing as this, except we have a square root of t. That's going to be equal to pi over 2 times 1 over square root of t times t minus 1. Yeah, right? Yeah, okay, that's correct. All right. And actually, I'm going to rewrite that even further. No, I'm not. I'm going to leave it like that for now and perform the new work over here. But anyway, that's valid for f prime of t. All right, so now we need to integrate both sides to get back to f of t. All right, so what would that give us on the left-hand side? Well, it would just give us f of t, and then that's going to be equal to, all right, we're going to factor out a pi over 2 and combine these into one integral and then use another trig sub. A lot of you would probably like to just do them out separately. I'm going to combine them into one integral just so I can use the same substitution on both. I just find it cleaner. I don't know why, I just do. So let's see, that's going to be pi over 2 times the indefinite integral, don't forget indefinite integral of, let's see, let's change this to a, let's see, that's going to be a square root of t over the square root of t times t minus 1. So we're going to have square root of t minus 1 over square root of t times t minus 1 dt. And that integral looks crazy. It's actually not that bad to do. Using the substitution that t is equal to sine squared theta. All right, let me make sure I have that right. We have the factor of pi over 2 factored out, and then we have square root of t over square root of t minus 1 over, yep. Yeah, that's right, okay. All right, so let's go ahead and make the substitution that t is equal to sine squared theta. All right, what does that give us? That gives us dt is equal to 2 sine theta cosine theta d theta. All right, so let's rewrite our integral. So we have f of t is going to be equal to pi over 2 times the integral of sine theta minus 1 over, let's see, that's going to be sine theta. This is sine squared theta minus 1, which is negative cosine squared theta. So we have a negative cosine squared theta. And then for our dt, we have a 2, which will cancel out this 2 right here, giving us just negative pi. Negative pi, so we've taken care of that 2. Now we'll take care of this sine theta just by getting rid of that, and we'll take care of this cosine theta by getting rid of one of the powers on the denominator here. And then we have d theta. All right. Just to make things a little bit nicer, I'm going to call this 1 minus sine theta to get rid of this negative sign in front of the integral. All right. So now we have f of t is equal to, let's see, pi times the indefinite integral with respect to theta of secant theta. Well, that is the absolute value of secant theta plus tangent theta. All right. And then we have minus pi times the antiderivative with respect to theta of tangent theta. And we know that that is the absolute value of secant theta. All right. Now we need to anti-substitute back in for theta. We need to get theta back to t. All right, so based on our triangle, what does our triangle look like with the substitution t equals sine squared theta? Well, we don't ever like to have an angle squared, so we'll take square root on both sides, giving us sine theta is equal to the square root of t. So let's do that. Sine theta is square root of t. There we go. So that means this would be the square root of 1 minus t. All right. And this is our theta. All right, so what does secant theta become? That is 1 over the square root of 1 minus t. Tangent theta is square root of t over square root of 1 minus t. So we'll just go ahead and put a plus square root of t there. And then this, of course, becomes 1 over the square root of 1 minus t. And these absolute values are very important in this problem, since we will be dealing with complex numbers. So we really need those absolute values, because we know we are not going to be getting, we are going to be getting back a purely real number for an answer for I. So we need those absolute values there. All right, using the properties of logarithms, we can just take this part times the reciprocal of this part, which will just have the effect of, well, let's see. If we multiplied this by the square root of 1 minus t, we would just get 1 plus the square root of t. There we go. So 1 plus the square root of t. So that's it. There's our f of t, right? Nope. Yeah, I bet a lot of people would forget that. And just as a quick note, when I made this substitution, I've actually attempted this one twice before, and I was pulling my hair out because I always put sine squared minus 1 as cosine squared theta, and I could not for the life of me figure out where I was messing up my sign, and that was it. It turns out that was it. I mistakenly put sine squared theta minus 1 as cosine squared theta, when in fact it's negative cosine squared theta. So don't make that mistake, and don't make this mistake. You need that plus c. Most of the time you need the plus c. You always have to account for it. It turns out in this case that since f of 0 is equal to 0, it's pretty easy to see that c is 0. So we'll just go ahead and put our f of t. The final value for f of t is simply equal to pi. So maybe some of you didn't notice this yet, but this is actually, oh, that's true. It's pi. Now it's pi times the natural log of 1 plus the square root of t. Of the absolute value of 1 plus the square root of t. My apologies there. All right. So that's pi times the natural log of the absolute value of 1 plus the square root of t. All right. All right, so let's go ahead and find out what our actual answer is. So that means that I is going to be equal to our function evaluated at I plus our function evaluated at negative I. So that's going to be equal to pi. I'll just factor that out because we're going to get 2 factors of pi there, or no, 1 factor of pi in each. And then that's going to be the natural log of absolute value of this evaluated at I times this evaluated at negative I. So we're going to have 2 terms here. We're going to have 1 plus the square root of I and 1 plus the square root of negative I. Well, I mean, technically that's a valid answer, but it's not very nice. So let's go further with it and actually find out what the absolute value of this mess is. First step we're going to do is we're just going to FOIL this out. So what does that actually become when you FOIL that out? Well, that's going to be 1 plus the square root of I plus the square root of negative I plus the, let's see, we have 2 square roots, so it's going to be a square root of, we have a negative I squared. I squared is negative 1, that just becomes 1. That whole thing is a 1. making this a 2. All right. Can we do better? Yes. Let me put this in there first. Let's see, that's 2 plus the square root of I plus the square root of negative I. All right, so we're still good. All right, but let's find out what the square root of I is. Don't forget we're taking absolute values, so it would be nice to express this in a rectangular form, like a plus b. All right, so let's figure out what that would be. Well, let's see. The square root of I, if this is our imaginary axis and this is our real axis, the square root of I would be about right here. And let's see, this distance would be the square root of 2 over 2. This distance would be 1, and this would also be the square root of 2 over 2. So let's see, the square root of I can just be written as square root of 2 over 2 plus square root of 2 over 2I. All right, now let's find it for negative I. I won't actually redo it on here. But you will find that the square root of negative I, because this would just move down here and this would become a negative square root of 2 over 2. So this is just going to be equal to the square root of 2 over 2 minus square root of 2 over 2I. I hope that's pretty clear. I'm sure it is if you dealt in any way with complex numbers. All right, so let's rewrite that. So now we have this whole thing becomes 2 plus this. We have square root of 2 over 2 plus the square root of 2 over 2I plus the square root of 2 over 2 minus the square root of 2 over 2I. This and this cancel. This just becomes a square root of 2, giving us I is equal to pi times the natural log of, we don't need the absolute values anymore, of 2 plus the square root of 2. Let me double check that. Pi times the natural log of 2 plus the square root of 2. That is correct. There you go. Well, everybody, hope you enjoyed that video. Happy New Year, and I'll see you next time.